Okay, thanks for coming out on a rainy day. It's good that you came. This is a critically important day because we're talking about constant rate of change. This is like the core idea of calculus. So we really want to get it. So you may have cranked out numbers in the past and called it a rate of change, plugged into a formula, but we really want to understand the idea and know our way around it, okay? So we really want to understand it. And that's what our goal is. So we'll do our best. Ready to start? So to start, let's just take a step back and just talk about what is the meaning of quotient. When you divide two numbers and you get an answer, what does that number mean? So here's an example. Suppose quantity A has a value of 17 and quantity B has a value of 5. It's very generic. If we took 17 divided by 5, which would give us 3.4, what would be the meaning of that number, 3.4, relative to the quantities A and B? So think about that. Maybe talk to the person next to you. What would 3.4 mean relative to quantity A and quantity B? Okay, so take 30 seconds or a minute. So what would that mean, 3.4 or 17/5? So if you're talking about quantities A and B, what is 3.4? What did you come up with? What does that number mean? Okay, that's true. So, and then what does that give you? What's the meaning of it? Yeah. So that's the result when you take quantity A divided by quantity B. Okay, so right, so talk about that in terms of the quantities. He's saying it's how many times 5 can go into 17. So what does it mean for the quantities then?
How many times B goes in A?
Okay.
3.4 goes into A.
Okay, what were you going to say? Did you raise your hand before?
Oh yeah, there's.
So you're all kind of talking about the operation. You're also kind of talking about division. All right, so 3.4. So if we have 5 of quantity B and 17 of quantity A, then what is 3.4 relative to those two quantities? Yeah.
It's how many times bigger B is than A.
Did you hear that? Did you hear what he said? Say it louder.
It's how many times bigger B is than A.
How many times bigger B is than A? He's got the right idea, but just the other way around. Yeah. So this is how many, it's exactly right. It's how many times bigger Isn't that true? How many times larger quantity A is than quantity B? That's what you get when you divide the amount of quantity A divided by the corresponding amount of quantity B. The result is how many times larger quantity A is than quantity B. Okay, another example. Suppose every 40 milliliters of water poured into a container causes the height to increase 7.5 centimeters. So consider 7.5 divided by 40, which is this quotient, 0.1875. What's the meaning of that in terms of the volume and the height? Tell your partner, go. Take a minute. What is the meaning of 0.1875 in terms of the volume of water and the height of water in the container? Go. anyone for this part of the room over here? Any ideas? What does the number 0.1875 mean for this volume-height relationship?
Isn't it just the opposite? That's just how much smaller the number is compared to the 40. 7.5 is 0.1875 is smaller than 40.
She said that 7.5 is 0.1875 of 40. 0.1875 is how many, the fraction of 40 that is 7.5. Okay? So what about in terms of volume and height? So we can talk about in terms of volume and height. Yes, sir?
Well, the units would be centimeters per milliliter.
Okay.
So it's saying for every milliliter, just how many centimeters per meters is rising up. So 0.1875 centimeters per milliliter.
0.1875 centimeters for every centimeters of rise for every milliliter added. Yeah?
I think it says like every 40 milliliters it increases 18%. That's the ratio of the point.
18% of what?
18% of the 40 milliliters.
Okay, so yeah, so the increase in height is 18% of how much water we put in.
The rate at which the water rises.
Okay, yeah, okay. So, exactly, right. All right, so this is really measuring the change in water height in the units of change of volume, isn't it? It's saying if we let the amount of volume, like he said, if we let the amount of volume, 1 milliliter, be our unit, so for every 1 milliliter of volume, how much does the height change? 0.1875 of that. 0.1875 of 1 milliliter is the amount of change. So we're measuring the change in height in terms of the change, or in units of the change of volume. Which he said is the rate of change. So what is rate of change? It's the same idea as this. It's relative size. Relative size. How large is this change in height compared to a change in volume? Compared to a change in volume, the change in height is 18% of that, or 0.1875 of that. Okay? So it's this idea that the quotient is relative size. How much relative to 1 unit of volume, what is the size of the change in height? Or how much larger is one than the other? How much larger is height than volume? Well, it's 0.1875. It's actually a fraction of volume. Okay. Does it make sense? Really important idea. Okay, so there's two parts to the idea of constant rate of change. And the first part is you got to have two quantities changing together. You got to have two quantities changing simultaneously. You can't have rate of change with just one quantity. Rate of change necessitates two quantities changing together. We call that covariation. Remember, we call that covariation. All right? But then it's a special way that these two quantities change together, a very specific way. It's such that changes in one quantity are proportional to changes in the other. So there's lots of ways that two quantities can change together. Constant rate of change is a very specific way, and it's characterized by this. Changes in one quantity are proportional to changes in the other. Okay? Let's go back here. All right, so changes in one quantity are proportional to changes in the other. And so we know by what we learned about proportionality, therefore there's this constant multiple. So if you take a change in one, it's always a constant multiple times the change in other. That's one of our definitions of proportionality. The delta sign will always mean for us a change in, okay? So every change in y is a multiple or a constant multiple of its corresponding change in x. That's proportionality, right? That's proportionality. So therefore, what does k equal? Simple math here. K is what?
Change in y or change in x.
It's a quotient, right? That's why we started talking about quotient. Because k is a quotient, it's the change in y over the change in x. Every change in y has the same relative size relative to its corresponding change in x. So remember what we said the quotient means. It means relative size. It's measuring change in y with the unit of the change in x, or how much larger the change in y is than the change of x. Relative size. So that value k, that constant multiple, is the relative size of the change in one quantity to the change in the other. Anybody have a question? Yes, ma'am. Sure. So while I'll just. So K is measuring, again, just to repeat it, measuring delta y in units of delta x. Relative size. How much k, the value k is how much larger changes in y are compared to changes in x. That's where we started over here.
So, I mean, it's going back to a slope as well. You compare it to the slope.
Yeah, we're getting there. Okay, can I go on? We're going to skip this slide. And we're going to skip this slide. Here we go. So, after a car goes under a bridge, it travels at a constant speed of 65 miles per hour, meaning that the number of miles it travels for some period of time is always 65 times the number of hours in that period of time. So what I want you to do is with your partner, in this situation, so what did we say? We said that delta y, in the last slide, equals what? K delta x, right? So, in this situation, what is delta y? So, everyone's going to think about it. So, what phrase or part of this paragraph would you say that's talking about delta y? And then what phrase or part of this paragraph would you say that's talking about delta x? And then what's k? So, I'm going to underline and circle in a second here. So you imagine, and compare with the person next to you. What in that paragraph is delta y? What is delta x? What is k? Okay, take a minute or two. Talk with the person next to you. Okay, someone in the back 2 rows. What'd you come up with? for delta y? What do you think delta y is? Okay, she wants to do it.
Delta y is the number of miles traveled.
So she's saying that delta y is this. She wants that to be delta y. What do we think? Agree? Something else? Okay, what about, so we're saying this. Okay, what about delta x? Somebody else, how about in the back two rows? What do you think delta x is in that paragraph? What phrase would be represented by delta x? Someone, yeah. She wants some period of time. Got some nods in the back, okay?
Number of hours.
Number of hours. Yeah, so that's the same thing, yeah. Uh-huh. So also this number of hours here. Okay, and then what is k? And according to the statement, then, the number of miles traveled is 65 times the number of hours, or some period of time. So, what's that? Should we switch delta y and delta x? So, is it okay if I do make delta x the hours in that period of time? Is that the same thing? Okay. Wow. Ooh, I'm glad it came back. Okay. That's cool. I want to do it again. All right. This is what I meant. Okay. All right. So, if delta y is k delta x, does it work? Is the number of miles traveled equal to 65 times the number of hours that went by?
Yes.
That's what it is. Okay, same thing. Same situation. So it's driven a while. Then the car is going to go another 0.3 hours at a constant speed of 65. And during that period of time, the number of miles the car has traveled increases by 0.3 of 65. In 0.3 hours, it's going to increase 0.3 of 65. Okay, identify in this situation. Same thing. What's delta y? What's delta x? What's k? Okay, what's delta y?
Number of miles.
Number of miles. Okay, delta x.
0.3 hours.
0.3 hours. And what's k? Still our 65. So we all know that 65 miles per hour is the rate, but can you see it now as distance measured in units of time? It's measuring distance in units of time. So our unit of time is 1 hour, so what's the distance traveled? 65. So it's measuring distance in the units of time. Or another way we talk about relative size. How many times greater is the number of miles traveled than the number of hours traveled? How many times greater is the number of miles traveled than the number of hours that we did that? 65, meaning of quotient, right? Meaning of quotient is relative size. And that gives us rate. It gives us how fast the miles is changing in the units of the hours or with respect to the hours. Okay, so what I want you to do is, let's go back. We ended up on a real nice example with the candles. We're on page 36. So we kind of did the first half of it together. I want you to kind of go through, review that again, and try to think of it in this mode of this kind of presentation that we just did. What is the meaning of quotient? What is the meaning of this delta y over delta x? Okay? And then go on to, there's kind of a second part which starts at part D. That's like the second half of it. Then I want you to work that also now in the context of what we just talked about. Really trying to apply these ideas. So as you're thinking it through, you're trying to apply these ideas of meaning of quotient and as rate of change, as relative size. Okay, and then I'm going to call you down to do a notebook check from a previous day. Okay? So you're working on page 36, number 2. Don't go on to number 3, just number 2. And let's have the A's and the B's. A's and the B's. Just bring your workbook down, make a line here. Okay, so I'll quickly do again what we did last time, which was, what did it say first? A change in time of 2 hours? Okay, how do we represent 2 hours going by from the time 3.5? Remember? So hours is the horizontal quantity. So 2 hours is going to be right there. So this right here represents change in time. So it might be delta t. And that delta t is 2. And in those 2 hours, how much did the candle decrease by? It decreased by 4.4. So 1, 2, 3, 4. So that's our delta H. And we said that that delta H is? Negative 4.4. Okay, over a time of 2. So what will the length of the candle be at that time? At which that time will be, so the time now, we've gone from 3.5 ahead 2 hours to 5.5. What's the length of the candle right there? 3.9, which comes from our starting height plus the change, right? Plus the change in the height. 3.9. Okay? So now it says represent a decrease of time. It's going back to that moment of time where it was 3.5 hours of burning. So we want to represent a decrease in time of 1.8. So starting here, what am I going to do? Decrease in time of 1.8. I'm going to go to the left, 1.8, right? Which takes me to what?
1.7.
That takes me to 1.7. So here delta t is 1.7. Or actually, it's not 1.7. What is it?
1.8.
It's not 1.8 either. Negative 1.8. Okay? In that negative 1.8 hours, how are we going to find what the change in candle height was over those 1.8 hours?
You need to find what the rate of change was from delta t to delta h.
Okay?
In the first
Okay.
section, which would be a negative 2.2.
Okay? And so, that, right, And that's actually the given, right? This right here is, if it's our rate of change, then how can we see it as a quotient and therefore as a measuring one thing relative to another unit? So where are we measuring there? Are we measuring height or are we measuring time with that 2.2?
Both.
And we're measuring one of those in units of the other. Which one are we measuring? It's height in units of time. We're saying 2.2 inches in the units of time. Okay? So that's our, am I on the screen still up here? So that is our, isn't that our K that we talked about? And what is that value of K? K is actually negative 2.2. For every 1 hour of time that goes by, our change in height goes down 2.2. So now we have a change in time of negative 1.8. How are we going to find the change in height? Yeah, so if it's 2.2 every hour and we have 1.8 hours, we're just going to multiply them. And what do you get when you do that?
3.96.
Say it again.
3.96, I believe.
3.96, which puts us at how far? So our delta H is negative 1.8 times negative 2.2. Actually, if we're following this up here, it should be the opposite of that. So negative 2.2 times negative 1.8, and that is our amount of change, which is, how much was that again? 3. Okay? And so, to get the new height then, we take the old height, which was 8.3, and add, which you said puts us at 12.26. So the 8.3, the old value of the height, plus the amount of change, equals the 12.26. Okay, any questions on this example? So then if you keep going, so the original length of the candle before it started burning, okay? Explain how you determine this value, represent the reasoning on your graph. So now your graph is a little, I think, doesn't quite showing up. You're going to have to kind of extend your axis, go up into the wording there. So how can we find what the original... So constant rate of change, graphs as, how does it graph? A curve? So those triangles that I drew, the blue and the red triangles, those aren't actually the graph. So as time goes by, we know the height is continuously decreasing, going through these points that we identified. That point, that point, that point. Okay? These triangles are critical to see how those quantities are changing together. As 2 hours goes by, the height goes down 4.4 inches. And so that's what that triangle is showing you. These triangles are all over the place in calculus. That's why we're doing them. Okay? Calculus makes great use of these as representations of change and changing together. Okay? So the question is then, at time 0, what is the original height? So the original height corresponds to time 0. Okay? So how can we do that? So how can we use what we're talking about to do that? Yes, sir?
We know what the height of the candle is at 1.7 hours.
Okay, so this is 1.7,
So we can
12.26.
find out what the height would be at 0 by multiplying 1 or negative 1.7 by negative 2.2.
Okay, so he's saying we want the time to go down now 1.7, and we want to see what the height would be if the time went down 1.7. And why? So y multiplied by negative 2.2.
To get the original height,
Okay.
which is what we did to get to 1.7.
Yeah, because what does 2.2 represent? Change in height every hour, and now we're going back in time how many hours? 1.7, so we want 1.7 times 2.2. And does that give us 16? So that 16 is our negative 2.2 per hour. We're going back in time 1.7 hours, and that gives us 16. So that's what the height would be at time 0. Any questions on this example? I want to get to the next one. Making sense? Okay. Oh no. Okay. So this next example, so there's a very nice picture of it. A little more artistic than mine, but okay, this one. So we want to bring the idea of slope into it. You guys have all on your math journey have all calculated slopes, and how did you do that? What is that?
Rise over.
Okay, rise over run, and so slope. She said rise over run.
Change in y over change in x.
Okay, so didn't you do y2 minus y1 over? And they told you, they said, this is the formula. So to find a slope, you just got 2 points, you just plug everything in, and you get a number. Okay? So what's our y2 here? 10.44. And our y1? How can we represent y2 minus y1 on the graph? On the graph there, can you represent y2 minus y1? Vertical or horizontal? Vertical, right? So right there, the length of that line represents 10.44 minus 5.16. Tell me what the value is?
5.28.
But we were calling 5.28 something else. What is y2 minus y1? That's just another way of saying what? Change in y, delta y. Okay? How do we represent the change in x? So this is going to be 5.1 minus 2.9 equals 2.2. And that is just the same as? That's our change in x. So what slope is finding change in y over change of x? Let's get that number. Tell me what that is. 2 point what? So slope is, it's
You got 2.4.
do something else?
2.4.
I'm hearing some different things here. So 5.28 divided by 2.2. 40? 2.4. Okay. So what does that number, the slope, now has meaning for us? What is the meaning of it?
Every 1,
It's k, right?
every passing of 1 is it rises.
So every passing of 1 in what quantity?
X.
So we're measuring what in units of what? We're measuring the change in y in the units of change in x, meaning if we change x1, always, y is going to go up by 2.4. If I change x2, y will go up 4.8, proportionality, right? If I change x by 10, y will go up how much? 24, proportionality, okay? And so y is always goes up 2.4 times as fast as x increases. Y is always increasing 2.4 times as fast as x increases. Relative size, right? Relative size. That's what rate of change is, relative size. How fast y is increasing relative to x. And visually, that's shown how? 2.4 we originally calculated as the slope of the line. The slope of the line is the relative size of y to x, or it's how you measure y in units of x. So that it's like there's so many different ways to look at this. Rate of change, relative size, slope. They're all, it's like if a coin had 3 sides, it'd be the 3 sides of a coin, okay? Okay, so why don't you, I'll check a few more notebooks. You can start and do B through D. Keep going on that one. Okay, 5 minutes left. So how about M's through P's? M's through P's, come on down. Last name? Write everything down. Next, last name. Okay, great. Last name? Gotcha. Last name? Jennifer? Okay. Okay. Last name?
Price.
Okay. Last name? Okay. Last name? Okay. Okay. Last name? Megan? Okay. 29. Last name? With an N?
Yes.
Okay. That's a lot more than that. Make sure you show it all. What's your last name? Gotcha. Okay. That's good. Gotcha. Last name? You're the one I saw on the street the other day? What? Did I see you on the street the other morning? Someone yelled at me and I didn't recognize them.
Wasn't me.
That was the day I showed up, so I didn't, yeah.
Last name?
Down the road.
29.
I mean, we're already at 2.
There's a lot more on that. What's the last name? Okay, gotcha.
I was wondering if I would check.
Let me show you after class. R through T. R through T. Last name? Corey? Page 29. Okay, we did a lot more there. So we should do everything. You got full credit. Last name. Show me 29. Nicole? Okay. Last name? Victoria? Good. Last name? Olivia? Gotcha. Okay. Good. Okay. Saunders? John? Okay. Last name? Okay. Gotcha. Let me just talk about notebook checks. So today I checked page 29, and everybody had something, which is good, but many of you didn't have nearly what we did in class. So on that graph, we were talking about proportionality changes, and I put lots of stuff on that graph, and then we answered the questions down below. So for many of you, going back and looking at that page, it's just going to be all, you'll have to go back to the video and watch that thing again. So make a good record of everything that I assign for you in class and everything that we do. It's really going to help you study down the road. Okay? I posted Wednesday's homework. Make sure you get going on that soon. It's a whole week's worth of homework. It's a lot of homework. So start this weekend if you haven't. Okay, if I haven't checked your notebook, come on down. Last name?
Riavia.
The last time I like didn't know.
Lauren?
Yeah.
Page 29. Okay. Say it again? Una?
Yeah.
Okay, gotcha. Welcome. Francisco? Okay, gotcha. Stuart? Victor? Okay. Yeah, so I think if you just go to...
I know that my grades thing, but like it doesn't show up on my class.
Oh, you can't even get to Blackboard?
Well, I can get the Blackboard, but you know, it's just like my grades, and like I can see like all that stuff section.
Oh,
Last
so maybe
time I checked.
this link is hidden from students. You're correct. Oh, those are my grades. Let's see.
Yeah, that one actually.
Let me turn it on to show it. Why isn't it doing anything? It's frozen. Oh, did I just click it off?
You just press it.
Where is it? Where? Okay, so my grades. Here we go. Show link. All right, try that now. If you still can't find it.
Grade on Blackboard now?
Yeah, sorry about that. I didn't realize that thing was off.
Oh, okay, cool. Because I was looking last night, wanted to know how I was doing, and or maybe it wasn't last night, but a while ago.
Okay.
There's 29. I didn't write
What's
that.
your last name?
Weber.
Okay.
Okay, thank you.
You're
I
welcome.
finally got my book.
Oh, good. That's going to make life better.
Yeah.
Okay. Oh, right. From before. What's your last name?
Oh, that's fine.
Last name again? Oh, E.
No big deal.
Starts with an E. This one?
Yeah.
I'm in.
I wish I would stop reading.
So I was checking. Okay. I was checking. Yes.
My jeans still aren't dry.
Good.
I know, I already tried it.
Okay. Almost. You just got one mistake there. How do you find 82.5% of Y? Close, but this won't do it.
I'll do it.
What doesn't work?
See you guys.
No.
Like 82.5
Is that what it is?
Is it?
Think about it.
Okay.
Think about it.
I'm on page 29.
Yeah?
I should be
Yeah.
there. Because I just got my book yesterday. So
Okay. Yeah, that's fine.
Okay.
You're good.
Can I just ask you a
Sure.
question? I'm always asking questions, I'm sorry.
That's great. I wish more people would.
Oh, it's a problem. Okay,
It's not a
so,
problem.
well, with the it's asking if the changes are proportional. All of these appear to be proportional because it's all like multiples of 7. But
What's
I don't
next?
really know where this sticks out here.
So this is great. This goes back to what we're talking about in class. So we got this change in time and change in distance. Okay, so what would it mean for those to be proportional? We talked about that earlier.
They need to share a common ratio or share a common multiple.
Right, so there needs to be some number that if I take the change in time and multiply it by that number, I always get the change in distance with that same constant multiple, and that's our k, right? So delta d, we're saying, is always some constant multiple of delta t.
Yeah.
Okay? And so is it?
Well, all of them appear to be except for that one. That one throws me off. So if that one is the only one that's not proportional, is none of it proportional? Or...
So it's always 7, except for the first one. So what's the change in time?
well, it depends on like the...
No, so tell me, forget about that.
Okay.
What's the change in time?
The change in time between those two?
Uh-huh.
It's... Well, it's 0, isn't it, at this point?
No, so this is saying the change in time between these two ordered pairs.
Oh, yeah. The change in time is 2.
And what's the change in distance?
14. Oh, did I just do it incorrectly? Let's see.
I think you just got those numbers wrong.
Oh, okay. So yeah.
Make sense?
Yes. Oh, and then can I ask one more question about what happened in class?
Sure.
At the very, I should have asked it when you asked if there were any more questions, but I guess I got scared. At this point, when it says the 16 is equal to negative 2.2 times negative 1.7, I multiplied those and it did not equal 16. So I obviously was looking at it from the wrong point of view.
Yeah, it sure doesn't, does it? Oh, well, that's, okay, what is that? So that's, yeah, I did that incorrectly. What is that? That is what?
The constant rate of change.
The constant rate of change.
Time multiplied by
times.
the change in time, right?
And so what does this really give us?
The change in y.
The change in y.
Oh,
Okay, and so where were we with y?
12.26.
12. So what are you going to do?
Okay.
What are you going to do?
You're gonna subtract, or not subtract, but you're gonna, part the change, or like add the change in y to.
So that wasn't really the 16. You're right. I wrote that was equal to 16.
Okay.
That's not right. So what is that really equal to? Or what? How do we use that to get the 16?
You multiply them together and then subtract that from 16, or add
That's
it to
it.
12.26.
Yeah.
Okay, that makes sense. So much more sense. All right. Thank you.
Okay, you're
And
very
what are your
welcome.
office hours again?
They're posted on Blackboard. There's a special link on Blackboard. Just click right on it.